Hello everyone. In today's lecture we are going to conduct a topic that is called as linear differential equations with constant coefficients, mainly useful in second year engineering mathematics as well as in the GATE examination. Here we are going to understand the topic which is written here, linear differential equations, more precisely linear differential equations with constant coefficients. In our earlier standard we understood how to solve differential equation with order 1 and degree 1. Now here we are going to understand how to solve the differential equation of higher order derivatives. Here I have taken differential equation of the type a0 d3y by dx cube plus a1 into d2y by dx square plus a2 into dy by dx plus a3y equal to fx. So this particular equation is called as linear differential equation with constant coefficient. First of all, you have to understand the meaning of the word linear. Linear means the power of dependent variable is always equal to 1. Here the relationship is of the type y equal to fx, and that's why y is dependent variable and x is independent variable. And when y is dependent and x is independent, derivatives are always of the type dy by dx or d2y by dx square or d3y by dx cube. Order can be anything. Just for the sake of understanding, I have taken maximum order as 3. This is a linear differential equation with constant coefficient. You can observe that here the coefficient of all the terms, derivatives or dependent variable, are constant, like a0, a1, a2, a3, etc. Now whenever we talk about linear differential equation with constant coefficient, you have to remember the points. Number 1, you have to remember that power of y should be 1. Number 2, the coefficient should be constant term. In other words, there should not be a product of variable along with the derivative. Means if there is a term of the type x dy by dx, so this is not in the category of linear differential equation with constant coefficient. And also there should not be product of more than one derivative. Means here if it is dy by dx along with d2y by dx square, d2y by dx square along with d3y by dx cube, if there is a combination, then this is not called as linear differential equation of with the constant coefficient. So this is the example of our topic. Now we have to simplify it further and we have to understand how we are going to solve this differential equation. So here let us assume that d by dx equal to capital D. Now in this entire topic we are going to take capital D as the notation for taking the derivative. So remember that if there is any term related to capital D, means we have to take the derivative. And now this equation can be simplified in this manner. So a0 into d cube y plus a1 into d square y plus a2 into dy plus a3y equal to fx. Now from this LHS we are in a position to take y common. So let us take y common and then equation will get reduced to the form phi dy is equal to fx, where phi d is nothing but a0 d cube plus a1 d square plus a2 d plus a3. Why it is called as phi d? Because it represents a polynomial with variable d, and you will know that whenever there is a polynomial we are in a position to find out the factors of the polynomial. In our next stage of this lecture we are going to understand how we are going to factorize this phi d or polynomial. So phi dy is equal to fx. This is the short form of linear differential equation with constant coefficient. Now we have to see that how we will get the value of y, means how we are going to find out the solution. The solution of this differential equation is always to be found out in two parts. The first part is called as complementary function and second is called as particular integral. yc is nothing but complementary function and yp is nothing but particular integral. Now how we are going to find out this in two parts? Let us take one by one. yc means complementary function, means it is the solution of the differential equation when RHS is assumed as 0. So for time being let us take a differential equation of the type phi dy is equal to 0. And we know that if yc is its solution, it has to satisfy the equation. So let us replace y by yc, and therefore we can write down phi dy yc is equal to 0. Let it be equation number 1. Now yc is a complementary function and which always consists of arbitrary constants like c1, c2, c3 or a, b, c, whatever you want. How to use this we will see in the next part of this particular video. Next, phi dy is equal to fx. Now this is the differential equation when RHS is present. So phi dy is equal to fx and its solution is given by yp, means particular integral. Again same concept, if yp is the solution of phi dy equal to fx, it has to satisfy the equation. So we can write down phi dyp is equal to fx. Now equation number 1 and equation number 2 we have written. So equation number 1 means what? It is nothing but the solution when RHS is 0 and number 2 when RHS is present. Let us add these two equations. So if you do the addition of 1 and 2, so while doing the addition we can take phi d common. So phi d into bracket yc plus yp on RHS we can take 0 plus fx. And here we have written already that yc plus yp is equal to y, and this is the reason that total solution is nothing but yc plus yp, and phi dy is equal to fx is the original equation that we obtain. Therefore always remember that the solution of the differential equation phi dy is equal to fx is always to be found out in two parts. First of all we have to find out yc and then we have to find out yp. Now how to find out yc, that we are going to study in our next part. Let us see now how to find out yc. Yc means complementary function and yc is the solution of the differential equation phi dy is equal to 0. So phi dy equal to 0 is the given differential equation and whose solution is to be found out. Number of steps are: first step is to write down auxiliary equation. Auxiliary equation means phi d is equal to 0. We know that phi d is nothing but a polynomial which can be factorized to get the roots of the equation, and depending upon the nature of the roots we can write down the solution of this differential equation. Now what do you mean by nature of the roots? Either roots are real or roots are imaginary. If the roots are real, that can be repeated and that can be non-repeated, and if the roots are imaginary, and that can be repeated imaginary or non-repeated imaginary, or in certain cases you may have a combination of real and imaginary roots. We'll see everything in detail one by one. So our first step is to write down auxiliary equation phi d equal to 0 to write down to get these factors of the differential equation or factor of the polynomial phi d equal to 0. For sake of convenience, let us assume that phi d is equal to d minus m1 d minus m2 dash dash d minus mn, where there are as many as n roots of this differential equation. So roots are of the type, so if you want to factorize that you have to equate it to 0, and therefore we get d minus m1 equal to 0 means d equal to m1, d equal to m2, d equal to m3 dash dash mn. Okay, so whenever highest order derivative is nth order, then you will get as many as n roots. If the highest order is third derivative, then you will get 3 roots, and depending upon this nature we are going to write down solution. Now there are 4 cases of understanding this yc. So case number 1 we will take when the roots are real and repeated, or पहले हम लेते हैं non repeated. So when the roots are real and non-repeated, now in that case the solution is given by yc is equal to c1 e raised to m1x plus c2 e raised to m2x plus dash plus cn e raised to mnx. So this is case number 1 when the roots are real and non-repeated. What do you mean by real and non-repeated? That we will see. For example, if we get values of d as 2, 3 and minus 1, then we can write down yc as c1 e raised to 2x plus c2 e raised to 3x plus c3 e raised to minus x. you can change the order of writing down this equation. Means you can also write down c1 e raised to minus x plus c2 e raised to 2x, whatever you want. So that doesn't make any difference whether you write down e raised to minus x terms along with c1 or along with c2 or along with c3. So this is case number 1 when the roots are real and non-repeated. Let us continue with this case number 2 now, when the roots are real and repeated. So whenever roots are real and repeated, how to write down the solution? For all these solution, we are going to understand only the method of writing down the answer. We are not going in detail of the derivations of this solution. So when roots are repeating for 2 times, means if d is equal to m1 is equal to m2, okay, or we can say that m1 is equal to m2 but other roots are different. So m1 or m2, these two are equal roots. Then the solution is given by c1x plus c2 e raised to m1x, and if there is a presence of third root, then we have to carry out the same procedure as that of case number 1, that is c3 e raised to m3x plus dash dash. In other words, we can say that if the roots are getting repeated for 2 times, you have to make a group of c1 and c2, and you have to introduce x along with one of the constant, either c1 or c2. If there is a case of m1 is equal to m2 is equal to m3, then you have to make a group of c1, c2 and c3, and we have to take x square as the coefficient of the c1, x as the coefficient of c2, and so on. For example, I can say that if you take d is equal to 1 1 1, then solution is given by yc is equal to c1x square plus c2x plus c3 e raised to x. So let us proceed for case number 3 and then case number 4. Case number 3 is roots are imaginary and non-repeated. Whenever we get imaginary roots, you always have to use the formula minus b plus or minus under root of b square minus 4ac upon 2a to get the imaginary roots. And then imaginary roots are always in the form of alpha plus or minus I beta. So for sake of convenience, we will take that there are only 2 roots, but we may have more than 2 roots. Means 2 roots are imaginary and third root, fourth root may be imaginary, may be real. That we will understand when we take the example. So time being, you can consider that roots are in the form of alpha plus or minus I beta. Always remember that beta is all the time considered as positive term, and alpha may be positive, may be negative depending upon the conditions. So alpha plus or minus I beta is there. So plus or minus is the sign not for beta but it is for I. In other words, we can say that whenever roots are imaginary, they are always complex conjugates of each other. And then solution yc is written as e raised to alpha x in bracket c1 cos of beta x plus c2 sin of beta x. So this is the solution of case number 3 when the roots are imaginary and non-repeated. Now we will see case number 4 when the roots are imaginary and repeated. In short, we can write down d is equal to alpha plus or minus I beta, alpha plus or minus I beta. Means the roots are getting repeated for 2 times. In all, there are 4 roots, and if there are 4 roots, we have to write down yc up to c1, c2, c3, c4, and therefore yc is written as e raised to alpha x as it is outside. And now we are going to use the concept of our case number 2 in which roots are getting repeated. We have to make a group of 2 constant terms along with x. So yc is equal to e raised to alpha x in bracket c1x plus c2 into cos of beta x plus c3x plus c4 into sin of beta x. So these are all about our 4 cases that we have seen in detail. Now let us see how to use these cases in combination. Number 1, for example, if I take d as minus 1, 2, 3, and let us take one more, that is 4. roots are real and non-repeated, and therefore we are going to use case number 4 to write down yc as. So it is c1 e raised to minus x plus c2 e raised to 2x plus c3 e raised to 3x plus c4 e raised to 4x. Let us take number 2. If I get d is equal to 2, 2 and minus 4, it means that two roots are repeated and one is different or non-repeated. In all, there are 3 real roots. It means that we have to use now case number 2 to write down the solution as yc is equal to. Now it doesn't make any difference whether you are going to write down minus 4 first or 2 first. If you want to write down 2 first, we have to use case number 2, c1x plus c2 e raised to 2x plus c3 into e raised to minus 4x. So case number 2 is now used. Let us take example number 3. For example, d is equal to minus 1 plus or minus 3i. Now roots are real and roots are imaginary and they are non-repeated. So value of alpha and beta are always real. So alpha is minus 1 and beta is equal to 3. So roots are imaginary. So yc is equal to, according to formula, e raised to alpha x means e raised to minus x, and in bracket we can write down c1 cos of 3x plus c2 sin of 3x. And let us take one more. If d is equal to plus or minus 2i, 2 and 3. Now let us take the combination of case number 1 and case number 3. Here we can observe d is equal to plus or minus 2i means 2 roots are imaginary and remaining 2 roots are real. Alpha is equal to 0 and beta is equal to 2 here. So yc is equal to, again it's up to you now whether you are going to write down plus or minus 2i first or 2, 3 first. I am going to write down plus or minus 2i. Since the alpha is equal to 0, if you take e raised to alpha x means e raised to 0x, that is 1, no need to write down. So we can write down c1 cos of 2x plus c2 sin of 2x as the value of beta is equal to 2, and that's why cos 2x and sin 2x are to be written there. And then plus c3 e raised to 2x plus c4 e raised to 3x. So this is the way of using all these 4 cases while writing down the solution. So as far as yc is concerned, we have taken everything in detail, how to find out yc or how to write down differential solution of the differential equation when RHS is not present, and whether RHS is present or whether RHS is not present. yc is first part of the total differential equation or total solution of differential equation. Now we are going to study how to find out the solution, particular integral or yp, or second part of the total solution. Now to find out yp, remember that there are 3 methods of finding out yp. Number 1 method is called as general method, number 2 method is called as shortcut method, and number 3 is called as method of variation of parameters. Now we will see case number 1 of shortcut method today. When the shortcut method is to be used, always remember the name suggests shortcut. Shortcut doesn't mean that you will get the answer in 2 steps. The shortcut method is name given just because this is applicable for the particular function. So we will see in detail now what do you mean by shortcut methods. Let us see now how to find out yp. As I told you earlier, there are 3 methods: general method, number 2 is shortcut method, and number 3 is method of variation of parameters. In our earlier part of this lecture, we have written there phi d yp is equal to fx. Yp is the solution when RHS is present, and therefore yp satisfy equation phi dy is equal to fx. From this we get yp is equal to 1 upon phi d into fx. So this is the formula of finding out yp. 1 upon phi d is called as inverse operator. So you have to remember this name. 1 upon phi d is inverse operator. Now let us see that how this shortcut method is used. General method and method of variation of parameters are to be used only and only when shortcut methods are not applicable. So let us see case number 1 of this shortcut method. There are as many as 7 cases of shortcut methods. Out of that 7 cases, we are going to study case number 1. Why this is called a shortcut method? Because these methods are useful for a particular function like exponential function or sine or cos function or x square, x cube, that is polynomial, or even a product of algebraic and trigonometric term, and various cases are there. So time being, we will see that case number 1, which is applicable for the function fx is equal to e raised to ax. So how to use this? Let us take one by one. So yp is equal to 1 upon phi d e raised to ax. In this shortcut method, we just have to replace this d by a. The meaning of a is coefficient of x in the exponent, and the solution or yp is given by 1 upon phi a e raised to ax. So this itself is shortcut method just by replacing d by a. But remember, since phi d is in the denominator, so whenever we are going to replace d by a, this phi a should not be equal to 0. Now if phi a is equal to 0, then it is called as case of failure. And in this case of failure, what we have to do? Let us see that. We have to write down x there, and then we are going to take a derivative of phi d, and then we are going to replace d by a. So phi dash of a e raised to ax, and again we are going to write down phi dash of a is not equal to 0. Now whenever we write down x into 1 upon phi dash of a, remember that this is a two-step process. Means in first part we are going to take a derivative of the function or of the equation phi d with respect to d, and then we are going to replace this d by a. Now further, if phi dash of a is equal to 0 further, so further I can write down if phi dash of a equal to 0, this is also called as case of failure. In short, I have written C of f, means case of failure. So in that case, again we are going to introduce one more x, and we are going to write down that as x square 1 upon phi double dash of a e raised to ax, and then again we are going to write down that is phi double dash of a is now not equal to 0. Okay, and then we can continue up to the term up till you get the finite term in the denominator. Okay, denominator should not be 0, non-zero term in the denominator. Up till that you can continue. Now this can also be used whenever f of x is a constant term. Why it can be used here? This constant term can also be written as, if k is a constant, k can be written as k into 1, and 1 means e raised to 0x. If e raised to 0x is written, value of a becomes 0, and then we can write down yp is equal to 1 upon phi d k into e raised to 0x, and therefore we can replace this d by 0, and therefore we can write down final answer as k upon phi 0. Generally, whenever there is phi 0, generally denominator doesn't become 0, and if it becomes 0, then we are going to follow the same procedure whichever it is explained in the earlier part of this case number 1. Okay, so there are 2 points we have seen. Number 1, when fx is equal to e raised to x, and number 2, when fx is equal to k. So fx equal to k is nothing but the application of this case number 1. Let us see now how these formulas can be used while solving the example. Yp is equal to, for example, if it is d square minus 5d plus 6 into e raised to 3x. Now in this case, what we are going to do, we just have to replace d by a means coefficient of x in the exponent. In this particular example, you can see that value of a is 3. So replace d by 3 orally. If you replace d by 3, you will come to know that denominator is becoming 0. It means that here it is a case of failure. So in case of failure, what we do, that we have to introduce x here, and then we are going to take the derivative of the denominator with respect to d. So d square minus 5d is to be differentiated as 2d minus 5 e raised to 3x as it is. And now we are going to check if you replace d by 3 whether you get 0 or non-zero term. Clear cut we can observe that if you replace d by 3 you are getting a non-zero term. So 2 into 3 minus 5, and therefore we get x into e raised to 3x. So this is the way of finding out yp using case number 1. Let us take one more application here. If yp is equal to 1 upon d square plus 7d plus 6, 5. 5 means it's a constant term. So if it is a constant term, how to write down? I already explained this concept to you. Whenever constant term is present, we have to multiply it by 1, and 1 means e raised to 0x. Now value of a is equal to 0. So you just have to replace this d by 0. So if you replace this d by 0, we get 0 plus 0 plus 6 as it is, 5 into e raised to 0x, and therefore we get final answer as 5 by 6. Let us take the example d2y by dx square minus 2dy by dx plus y is equal to e raised to x plus 1 whole square. Now we are going to understand this example in detail and how to take the steps, that also I will tell you one by one. Your first step is to assume d by dx as capital D. So replacing d by dx as capital D, we get d square y minus 2dy plus y is equal to, we can also expand RHS at the same time. It is in the form of a plus b whole square. So first term is e raised to 2x plus 2 into a raised to x plus 1. From LHS now we have to take y common. So therefore d square minus 2d plus 1 into y, and now RHS must be written as it is. Next step, auxiliary equation. So whenever we find out the total solution, we have to find out yc and then yp. So for yc we need to write down auxiliary equation. The meaning of auxiliary equation is we have to equate this polynomial to 0 to find out the roots of the equation. We can see that it is nothing but d minus 1 whole square, and therefore we get two roots of the equation as d equal to 1 and 1. Out of that 4 cases, it is now case number 2 of finding out yc, and that is roots are real and repeated. So when the roots are getting repeated, we can write down yc is equal to c1x plus c2 into e raised to x. Let it be equation number 1. So half of the example is completed. That complementary function means yc is now with us. We will find out yp now. So yp is given by 1 upon d minus 1 whole square e raised to 2x plus 2 e raised to x plus 1. Now in RHS there is an addition of 3 terms, and that's why denominator must be splitted into 3 parts. So 1 upon d minus 1 whole square e raised to 2x plus 1 upon d minus 1 whole square 2 into e raised to x and plus 1 upon d minus 1 whole square. Now we can observe that here we just have to replace d by a. Now value of a in first term is 2 and value of the second term is 1. We have to replace d by a. So when you replace this d by 2, doesn't make any difference, denominator is not becoming 0. But as far as this term is concerned, if you replace d by 1, denominator is 0, and there is a case of failure only for the second term. And that's why I have written below just to understand that there is a case of failure. So continuing this, so 1 upon 2 minus 1 whole square e raised to 2x as it is. Now we know that in case of failure, what do? We have to introduce x and we have to take a derivative of the denominator. So derivative of d minus 1 whole square is 2 into d minus 1 and then 2 into e raised to x as it is plus 1 upon d minus 1 whole square. And also we know that whenever there is a constant term 1, we have to replace 1 by e raised to 0x. First term is now totally simplified, e raised to 2x upon 1 square, and the second one still there is a case of failure, and that's why we are going to introduce one more x and that becomes x square. This 2 is cancelled now and derivative of d minus 1 is 1 and then e raised to x to be written as it is. Now as per the concept of case number 1, we're replacing d by 0 now. So if we replace d by 0, so we get 0 minus 1 whole square into e raised to 0x. And now we can write down final answer of yp as e raised to 2x plus x square into e raised to x plus last term is now 1. So we can mark this as equation number 2. And final answer, final solution, y is given by yc plus yp. And therefore, just adding equation number 1 and equation number 2 to write down final answer as c1x plus c2 e raised to x plus e raised to 2x plus x square into e raised to x plus 1. So this is the solution of given differential equation, which is a second order differential equation with constant coefficient. So this is a linear differential equation with constant coefficient, and how the solution can be found out, that I have explained very much in detail. So thanks a lot for joining with us.